Welcome to the European Southern Observatory. In this video, we will provide a general introduction on interferometric observations with the Very Large Telescope Interferometer, or VLTI. The VLTI can achieve millisecond resolution by combining light from 4 telescopes. This high resolution allows, for example, to accurately measure stellar diameters, study the morphology of circumstellar environments, as well as the inner structures of active galactic nuclei. The VLTI operates with 2 types of telescopes: the fixed 8.2 meter unit telescopes, or UTs, or the movable 1.8 meter auxiliary telescopes, or ATs. The system works by sampling incoming wavefronts and recombining them to produce interference fringes, with delay lines compensating for the optical path difference, or OPD, between the beams. The angular resolution achieved by the VLTI is determined by the observation wavelength and the projected length of the baseline. That is the geometrical arrangement of the 2 telescopes used for observation, with the smallest resolvable scale being proportional to wavelength divided by baseline. The VLTI uses 4 telescopes simultaneously, for a total of 6 baselines. While UT baselines are fixed, ranging from 46.6 meters up to 130.2 meters, the ATs are movable. AT baseline configurations are requested using generic names: small, medium, large, and extended. Since changing an AT configuration requires physically moving the telescopes, this process can take up to 2 days. The performance of the VLTI relies heavily on advanced adaptive optics, or AO systems, NAOMI and GPAO. When using the ATs, the AO correction is handled by NAOMI, the new adaptive optics module for interferometry. This system delivers a stable and high Strel ratio, which is crucial for achieving more robust fiber coupling and improving the sensitivity and precision of the interferometric data. In service mode, NAOMI can guide on stars as faint as 12.5 magnitude in G-band, depending on atmospheric conditions. NAOMI also provides fast chopping capabilities to aid instruments like Matisse in subtracting thermal background. When operating the UTs, the AO correction is provided by GPAO, the Gravity Plus Adaptive Optics. This is a high-order, laser-assisted AO system used with the UTs, which commands deformable mirrors and increased fiber coupling and instrument sensitivity. GPAO offers multiple modes using either a natural guide star, or NGS, or a laser guide star, or LGS. The NGS visible mode has a limiting magnitude of GRP of 12.5. The LGS visible mode is essential for providing high-order correction when natural guide stars are too faint, enabling corrections for stars as faint as GRP of 17. However, even when using LGS modes, a natural guide star is still required for performing low-order corrections. GPAO also provides near-infrared capabilities with the NGS infrared mode, renamed from the former GPAO system, and the LGS infrared mode, which analyze light in the H and K bands for a limiting magnitude of 10 in K band. If the target is fainter than these limits, both NAOMI and GPAO offer the possibility to perform off-axis QD guiding if a guide star can be found within a radius of about 50 seconds from the sign star. For the exact limits, please refer to the VLTI user manual. Different types of interferometric observations are available and needs to be specified at phase 1. First, imaging, which uses multiple baseline configurations to uniformly sample the UV plane for image reconstruction. Second, snapshot observations are defined as standalone concatenations without further time links or requirements to fill the UV plane. Third, time series involve concatenations that are repeated over the observation period, typically over a few days in a row or 2 to 3 times per AT configuration. Fourth, astrometry, which specifically uses gravity dual field observations to extract astrometric information. For imaging observations, ESO provides a scheme to optimize operations for aperture synthesis with the VLTI. This scheme only applies to service mode proposals using ATs. It requires that proposals aiming at image reconstruction are marked as such using the imaging observation type in Phase 1 and Phase 2. In addition, such proposals should request time corresponding to a minimum number of concatenations per object and per AT configuration on at least 2 configurations. More details can be found in the VLTI user manual. The reason for this is to ensure a minimum reliability and dynamic range of the reconstructed image. Additionally, the VLTI AT telescope schedule includes the so-called imaging slots. These are periods of about 2 weeks of uninterrupted service mode time with flexibility on the exact dates of changing configurations within this slot. Imaging slots are primarily intended to support imaging observations, but they are not restricted to this type of VLTI observations. Most interferometric observations must be calibrated by observing a dedicated calibrator star immediately before or after the scientific target. A calibrator must have a stable and known angular diameter or be unresolved. The calibrator should be close to the scientific target in the sky and have a comparable magnitude. Tools like Calvin or GMMC's SearchCal are available to help users select appropriate calibrators. The details about the calibration strategy of the different VLTI instruments are described in the corresponding dedicated tutorials. Thank you for watching. More information about the VLTI instruments can be found in dedicated tutorials and on the dedicated online web pages. For any questions, please contact us at ESO User Support. Happy observing!